Hello, everyone. I see a pretty healthy audience today, so lots of interest in this conversation. So if you just joined us, hello, my name is Yen. I am the Executive Director at the Volta Foundation. We're a nonprofit supporting the growth of the battery industry. At today's event, our esteemed panelists here will discuss the lithium metal battery data, which was released by SES recently. Please keep in mind that more details and updates will be revealed in the upcoming SES third annual Battery World event, which will take place on December 12th. So without further ado, I'd like to introduce our panelists. First, I'd like to introduce Mr. Mark Newman. Mark is the founder of Electric Revolution Ventures. He is a renowned expert, advisor, and investor in batteries, semiconductors, and electric vehicles. Mark was the top-ranked analyst and lead author of Bernstein's all-time most read research globally, The Electric Revolution and the Battery Bible, and is a frequent speaker and commentator on these topics. Mark is an active investor in several startups and advisor to SES. He also advises other investors, including the Oxford Science Enterprises, and serves on the board of the Faraday Institution, which is the UK's flagship battery research program. Mark holds the master's in chemical engineering from University College London and an MBA from Harvard Business School. Next, we have Professor Billy Wu. Professor Wu is an associate professor at Imperial College London, where he co-leads the Electrochemical Science and Engineering group. At the group, he manages a multi-million-pound portfolio of projects which focuses on the interface between the fundamental science and engineering, as well as the application of batteries, fuel cells, and supercapacitors. Professor Wu received his PhD in electrochemical engineering and master's in mechanical engineering from Imperial College London, and has more than 10 years of experience working on battery technologies, having published more than 60 papers in the area, and he is also on the editorial board of journals such as Energy and AI and Science Reports. And finally, I'd like to introduce, welcome, Dr. Qichao Hu. Qichao is the founder, chairman, and CEO of SES AI Corp. SES is the world leader in the development and manufacturing of high-performance lithium metal batteries for automotive and transportation applications. And before we start the session, I'd like to mention that in case there's not enough time to answer all the questions during our 20-minute Q&A session towards the end, please feel free to contact SES via its LinkedIn page. All right, panelists, the stage is yours, so let's go to Mark.
Great, thanks, Yen, and I'd like to thank Volta for hosting this event today. As Yen mentioned, today we're going to be talking about the new updates from SES, and particularly the progress SES has made with their 100 amp hour lithium metal battery. So a bit of background here before we get started. A couple of years ago, SES released its 4 amp hour cell data, along with other due diligence that we had done prior to the D-SPAC combination. And this was the first time, I think, that any battery company had released so much data on its next generation battery cells. Last year, SES followed that up with another huge set of data, this time on the 50 amp hour cells. And just a week or so ago, SES finally released its data for the 100 amp hour cells, which we are going to discuss today. SES also recently announced the world's first automotive B-sample JDA for lithium metal batteries. So in a minute, what I'm going to do is I'm going to let SES founder and CEO Qichao Hu talk a bit about the 100 amp hour cells data, and also the new B-sample announcement. Then Billy and I are going to have a chance to chat a bit and discuss what we think this means, and ask questions directly to Qichao about some follow-up questions we've got about the data and B-sample, etc. We're then going to open up to questions from the audience. There is a Q&A function on Zoom, so it's probably at the bottom, depending on which device you're using. So feel free to click on that, and it should be open already, I believe. So you should be able to type questions in there, and we will get to those, as many of those as we can at the end. We probably have about time for about 20 minutes worth of questions, so should have plenty of time to get to many questions during then. Also, a reminder that SES will be presenting much more during the upcoming Battery World event on December 12th. And details of that will be shared in the chat function below as well. Or you can reach out to SES or one of us directly if you do not have information on the Battery World. And so with that, I'd like to hand over to Qichao to discuss a bit about the recent data and announcements, and then Billy and I will follow up with some questions for you. Qichao, over to you.
Thanks, Mark, and thanks, Billy. And it's good to be back here and then doing this data review with you guys. We did this before, and it's like our annual tradition. We released data on the 4 amp hour lithium metal cell back in 21, and then we released data on the 50 amp hour lithium metal cell last year, 2022, and then this year now we're releasing the 100 amp hour lithium metal cell, and also, like Mark mentioned, next week, December 12th, we will have our annual Battery World, and then we're going to announce this B sample. Back in 2021, we signed the world's first lithium metal A sample joint development with automotive OEM, and then we just signed the world's first lithium metal B sample joint development with automotive OEM. So we're quite excited. It's a lot of hard work. But we're quite excited about the progress. So, Mark, am I going to share slides, or someone on your side will?
Are you able to share the slides on your side, Qichao?
It's not letting me. Yan, do you have that?
Qichao, let's try again. I just promoted you to.
Okay, I'm gonna see this again.
We already have one question in before the slides have started.
Yeah. Okay, let's see this.
This is to prove that this is live, everybody.
Okay, can you all see?
Here we go. Yes.
Can you see? Okay. Yeah, so this is the 100 amp hour lithium metal pouch cell. It looks just like the 50 amp hour, but it's actually the 100 amp hour cell. And then this table is a summary of the 4 cells that we have released so far. So the 4.2 amp hour cell that we released back in 2021, the 50.7 amp hour cell we released last year, 2022, and then this 100 amp is 105.8 amp hour cell that we just released. And then we are showing data for the room temperature, energy density, low temperature energy density, that's 0 degrees Celsius, lifetime, cycle life. We referenced 3 cycling conditions, and also fast charge, safety, the standard for safety tests, and then the UN certification. So in terms of summary, if you look at the room temperature energy density, the 100 amp hour cell actually it's the highest. And then so the energy density decreased a little bit from 4 amp hour to 50 amp hour, and then increase back up again when we get to 100 amp hour. Some people ask why the 50 amp hour energy density is so low. Well, so the 50 amp hour cell was actually never meant to be a 50 amp hour cell. It's actually meant to be a 100 amp hour cell. Just we added half the number of layers. That's why the energy density is low, because it's designed to be 100 amp hours, but then we just added half as many stacks. But you can definitely use the 100 amp hour cell energy density as a reference. And then the low temperature at 0 degrees Celsius, and we also have the energy density. And then cycle life, we have 3 conditions: silver 10 charge, silver 3 discharge, silver 3 charge and discharge, silver 5 charge, and 1C discharge. And then fast charge, and then also safety, thermal null penetration, overcharge, and external short circuit. And then certification, so all 3 have received UN 30.3. So the first is these 100 amp hour cells. First is the low temperature performance. So this is at from room temperature, 25 degrees Celsius, all the way down to negative 30 degrees Celsius. And then we are testing at silver 3 discharge. So we can still get 80% capacity even at negative 30 degrees Celsius. This is actually quite consistent to the smaller 50 amp hour and 4 amp hour cell that we reported earlier. So this is low temperature performance. And then this is room temperature, but high power performance. So this goes from silver 10-hour discharge, all the way up to 3C discharge. That's 20-minute discharge. And we're able to achieve 90% capacity at 3C, 20-minute discharge. So at 20-minute discharge, we're able to achieve 90% of the capacity if we did at 10-hour discharge. So this is a very good high power performance at room temperature. And then in terms of safety, this is a null penetration. We can pass this test. There's no thermal runaway. This is actually done at a third party. This is overcharge, and also we pass. This is at a third party, and this is a 100 amp hour cell again. This is external short circuit. Again, we also pass, and it's at third party. And this is a thermal test, and again, we also pass, and this is also third party test. And then this is UN 30.3 summary that we receive of the 100 amp hour cell. Yes, that's basically a summary, and then we publish this data report on the website. So happy to go into more details with any of this.
Great. That's great, Zhiqiao. Before we dive in to some of the data, is there any questions you'd like to, any points you'd like to make about the recent announcement on the B sample JDA that was recently announced?
Yeah, so that's actually a very big milestone. And so we started this A sample back in 21, and then it took about 18 months. And then now we're entering B sample, and we expect to complete that by the beginning of 2025 timeframe. So we mentioned earlier, A sample is basically we finalize the cell chemistry in this cell format, and typically it's a large long pouch cell. And the B sample is now it becomes a lot more practical, and the OEMs will think about which vehicle, which brand they want to put this chemistry inside the vehicle, and then how do you price that? And then is it going to be a expensive car? Is it going to be $100,000 plus car? Is it going to be a $60,000 car? Is it going to be a $40,000 car? And then that will determine what cathode are we going to use. Is it going to be high nickel, or is it going to be LFP, or is it going to be some blend of the two? And are we going to use lithium metal so we can so LFP can compete with high nickel lithium ion in terms of energy density? So now we are getting into pack design, pack level design, so that we can meet the cost target, and then so the OEMs will set the cost target, and then we come back to the pack design, and then that will set the safety targets, the cycle life, the cathode material, the cost, and then we finalize the cell design. So A sample, we're still not sure about the chemistry, what electrolyte to use, what anode to use. Now the chemistry is more or less set. Now we are still fine-tuning the cell design based on the final vehicle and the final pack. So, and a lot of considerations are a lot more practical now. Back in A sample, we still did a lot of R&D level design, but now a lot of the requests are coming from the engineering team, the vehicle marketing team, and so it's the considerations are a lot more commercial and a lot more practical. And then some of the hurdles that we had to overcome to get into B were actually really hard. One is actually safety. So and I can talk more about safety later. When we talk about safety at this level, B sample, we're not talking about lab scale, like safety on paper. What we're talking about is actually very detailed, very specific, practical vehicle pack level safety now. And then we have this, we spent a lot of time finalizing the set of tests, safety tests, specifications and targets. How do you run the test at the cell level? How do you run the test at the pack level? And then exactly what outcome we're trying to achieve. And then we finally finalized that. And then we made a lot of progress improving the safety at the material level, at the engineering level. And then going forward in the B sample, we need to finalize and improve the safety even more. But we have demonstrated that we can at least achieve the practical safety that's needed to move into the B sample next.
Great, thanks for that. That's sounds very promising. So we'll come back a bit to discussing a bit about the B sample in a minute. I think before we do that, let's chat a bit about the data itself, and I'd like to bring in Billy, Professor Billy Wu from Imperial College London, to get your comments on what we've learned from SAS and from Qichao today related to this, so the data specifically.
Great,
performance
thanks, Mark.
data.
And fantastic to see Qichao again at this annual event. It's fantastic to see year on year that there's been some really exciting developments. So my reflections on the data is that having tested many different lithium-ion batteries from various manufacturers, that for a practical battery in any applications, we need a combination of characteristics. We need high energy density, we need high power, and good low temperature performance, to give a few examples, and we need them all in a single device. So my first reflection was that from this data set, it's really promising to see these really exciting numbers of 400 watt-hours per kilogram, which, to give a sense of context, a state-of-the-art lithium-ion battery, which arguably is starting to approach its theoretical limit, is about 250 watt-hours per kilogram. So we're already seeing at the gravimetric level a 60% improvement, which is really promising. At the volumetric level, 860 watt-hours per liter is again really promising. And lithium-ion is maybe at about 700 watt-hours per liter. And again, that maybe is about 20% improvement. The key about these high energy cells, which I'm particularly excited about, is normally in other high energy cells, not only do you get that, but the challenge is that as you go to low temperatures and high powers in some other systems, they start to drop off significantly. But we don't really see that in this lithium metal cell that SES has developed. And the fact that you retain 80% capacity at -30, that's really impressive. From some other systems, we see that often falls off a cliff in terms of accessible capacity, because often it's very difficult for the lithium ions to kind of move through the electrolyte and so on. Similarly, that high power performance of 3C, which is a discharge in 20 minutes, that's really impressive. So for a 100 amp hour cell, 3C effectively translates to 300 amps. And again, we normally see that drop off in other high energy dense cells. Also, the fact that we see all of these characteristics in a large form factor cell, I see that as being a lot of benefits for making large form factor cells. One, you reduce the number of interconnections in a battery pack, and therefore the weight of the battery pack, you would assume, has benefits there, and also points of failure. But the fact that you've achieved this in a large form factor cell and also passed all the safety tests is again really promising. I had a colleague once who said the bigger the battery, the bigger the boom. And obviously, as you make these larger and larger systems with advanced materials like lithium metal anodes, safety is a concern. That's not to say it's not surmountable, but the fact that you've proven at scale that you can pass these tests is really promising. I think when you look at next generation chemistries which are coming out, such as solid state chemistries, other ones which use silicon, they also show some quite promising results. However, the fact that we've got to a B stage now with SES is really promising, because when you look at some of the data from some other players, you can often tweak the composition to give you high power, to give you high lifetime, but often is a trade-off. So what we're looking for, hopefully, is for people to lock in their designs and show in a single battery, can you actually achieve all of these metrics? And from this data, I think it's very promising to see the beginnings of that. So those were most of my reflections, Mark.
Appreciate that, Billy. And I think it's just quite important just to double click on this point about the multiple conditions, right? So it's not just one, we're not just looking at one data point in isolation of the other data points. So we're looking at energy density at different C rates, different power requirements, and at different temperatures. And again, I don't think we've seen that from other companies, at least not on next generation batteries, at least not the amount of data we've got here from SES. And it's every year, the 3 years, we've seen quite a bit of data here. So I'd like to just applaud SES on this, and also you can notice, if you go back to that table, Qichao, at the beginning, how the energy density actually has improved on the 100 amp hour cells. So I noticed from the 4 amp hour cells that we were talking about 2 years ago, and in fact we were looking at this data before the before SES even went public through the DSPAC. Actually the energy density got actually slightly lower for the 50 amp hour cell, but for the 100 amp hour cell, energy density is higher than both of them. So that's I think interesting to point that out, and it's now 399 watt hours per kilogram, so right near that magic 400 level, which is extremely impressive. So Qichao, do you want to talk about, first question to you, do you want to talk a bit specifically about why we see that the energy density jump up quite a bit from the 50 amp hour cell to the 100 amp hour cell?
Yeah, so typically the cell level energy density should go up as you increase the capacity, assuming the same material, same loading, same everything. So when you go from 4 to 50 to 100, the energy density should go up. The only reason that the 50 was low, so the 50 amp hour was never meant to be a 50 amp hour. It was meant to be a 100 amp hour, and then but then we just fill half the number of layers. So the 50 is actually a 100 amp hour cell. I mean, it was designed to be a 100 amp hour cell. So the depth, the thickness was actually quite thick, but then we just filled it with half as many layers as we will put in a 100 amp hour cell. So the 50 amp hour cell, that cell design was very inefficient. That's why the energy density is lower than it's supposed to be. I mean, if we had designed a 50 amp hour cell, then the energy density will be similar to the 100 amp hour cell. But in this case, the 50 amp hour was a stepping stone to the 100 amp hour.
Okay, got it. That's
Yeah.
pretty clear.
Yeah.
That's pretty clear, Chiao. And should we talk a bit about the cycles here, and where are you right now with the cycling? We can see some numbers there, which and notably quite similar to the data you've got from 4 amp hour, 50 amp hour, and 100 amp hour. So that's clearly showing that you're keeping the cycles, and the cycles are not collapsing as you go higher, which is definitely encouraging, but it's still perhaps a little bit low compared to what car OEMs will be wanting. So would you like to talk a bit about that, Chichao, and also Billy, any comments from you on this would also be appreciated.
Yeah. Yeah, so the cycle life, again, these are all under simulated cycling conditions. No real driver would actually follow Silver 10, Silver 3, any of these protocols. Our target from the OEMs is actually 500 cycles, 500 cycles, and then different OEMs have different charge and discharge protocols. For example, some will want Silver 10 charge and Silver 3 discharge, and someone Silver 3 charge and Silver 3 discharge. So our target is 500, and then we're talking about full depth of discharge from 0% state of charge to 100% state of charge. And some OEMs that mention they want thousands of cycles, typically that's actually not full cycling, but for us it's full cycling, and then we are targeting 500 cycles, and we're actually getting quite close. And again, this actually depends a lot on the cycling conditions. For example, we have one other test that's actually not shown here. It's for eVTOL applications, so flying cars, where we did Silver 3 charge, and then we also did the actual user mission profile. In that case, we got more than 1,500 cycles. So these cycle life are these numbers that you're seeing are under very rigorous lab scale cycling test, and in actual use case, we expect the cycle life to be much longer.
Great, Chichao. And just to add to Mark's question around cycle life, I think we've seen some really exciting developments where you're actually producing these not just at large scale, but also in larger volumes as well. Can you maybe comment on, as you're producing these, some of the challenges with making consistent cells, and how consistent are these cells that you're making?
Yeah, so actually now our consistency has improved a lot. So one thing that's very important is the control plan when you build a cell, going from IQC, so the incoming material quality control, the cathode active material, the anode, the electrolyte, the separator. We took the anode in-house, but then the cathode, lots of these materials to the cell assembly plant. And a few months ago, we had a control plan with about 300 quality checkpoints. And actually now we have about 600 quality checkpoints. And we expect to get to more than 1,000. And in B sample, we expect to get to about 14 to 1,500 quality checkpoints in a control plan. That means when you build a cell from the incoming material quality control to the final cell coming off the line, there's is currently 600 control points. Soon will be 1,400 control points that we have to check. So once you implement this rigorous quality control plan, then you can really improve the consistency. And the one benefit of making these hybrid lithium metal cells is that the manufacturing process is quite similar to lithium ion, and we can really leverage a lot of the control plan that's been developed and improved and also matured in lithium ion industry for lithium metal. So we don't need to reinvent the control plan. We don't need to reinvent the manufacturing process, because once you reinvent the manufacturing process, then the consistency, all that becomes questionable. But for us, it's not easy. Some materials So some materials that were difficult to control, say working with vendors, then we took in-house. For example, this anode. Now we actually buy this thick foil, and then we process it to thin foil, and then we apply it onto our copper current collector, and then that's our anode. So it's a combination of leveraging a very mature control plan from lithium-ion industry, and then just systematically increasing the rigor of this plan from 300 to 600 to 1,000 to 1,400 points, and also mastering some of the key material manufacturing process in-house. It's a lot of work, but currently the consistency. So, for example, our 3 A-sample lines, for the 3 A-sample JDAs, we make about 1,000 cells per month per line, and most of these cells we put to test, and the performance are fairly consistent.
So on that, Qichao, I wanted to just touch on this topic of scalability and manufacturability a bit more. So, kind of, can you talk a bit more about manufacturability challenges? Where are you right now? You mentioned about the scale of your A-sample line. Can you talk, like, where are you today in terms of your capacity, in terms of how many cells you're spitting out per day, and where do you expect to get to in the next year or so? If you could talk a little bit about these manufacturability and scaling, that would be great, and especially considering the background of you've just moved to B samples, so there clearly must have been quite a few improvements here. And I know that you can only talk so much today because you're going to be talking much more about this on the Battery World event December 12th, but maybe if you could give us a bit of a taste for that now, would be great.
Yeah. So this is a key topic that we will talk about at the Battery World next week. So currently we have 3 A-sample lines, and then for the 3 A-sample JDAs, Honda, Hyundai, and GM, and then we consistently make about 30 cells a day, and then that's roughly 600 to 1,000 cells per month per line, depending on the schedule. And then, so these are the 100 amp-hour cells. And then we are preparing 2 B-sample lines, one in Shanghai, one in Korea, for two of the OEMs. And then so the A-sample line is basically we get to about 1,000 cells per month per line. I think that's the cap for the A-sample line. Once we get to B-sample line, our target is to comfortably make about 5,000 cells per month per line. And then actually one of the lines will also use for UAM, urban air mobility. And then so per month we can actually supply about 3 to 5 aircrafts worth of batteries for the UAM per month per line. And this is why the control plan is really important. So a year ago, when we just in the beginning of A-sample, we had separate control plans for Honda, GM, Hyundai, and then they're all very different, and they had a few control points, less than 300. And recently, we've systematically standardized and unified the control plan, and then now we're on to about 600 control points. Next year in 24, for the B-sample lines, we will get to 1,400. So I keep talking about this control plan because the control plan is so key to improving the manufacturability of our cells, regardless if it's in Shanghai or Korea and which OEM it is for. Once we have this unified, standardized control plan, then we feel confident with the quality of the cell. And this control plan is also tied to our avatar. So our avatar would take the cell design, the material design, the manufacturing quality data, and the test data, and then basically systematically monitor the battery health, and then can predict remaining useful life, and even sometimes incidents before they happen. In the past, we've had about roughly 24 or so incidents for these 100 amp hour cells, and we could predict, our avatar could predict 23 out of 25. So that's like that's a 92% accuracy, and then this is all because we collect this data. So a key part is really in this data collection and the data processing. If we don't have this, then we will not be able to go from A to B, and we will not be able to manage 5 lines, 3 A sample lines, and then 2 B sample lines. And also, in addition to the manufacturing lines, one really important capability is testing. So, for example, if you make 30 cells a day, 1,000 cells per month per line for A sample, and you have three A sample lines, and then you're going to make 5,000 cells per month per line for the B sample cells, you have thousands of these large capacity lithium metal cells. Where and how are you going to test these? So we've built these bunkers with hundreds to thousands of these large capacity lithium metal cell channels, so that we can safely test these cells and then collect this data. And then all these data are part of this control plan, which is tied to our avatar. It's a core platform that we've built over the past 2 years, basically systematically building this control plan and then tying it to the avatar, so that we know what we're making, and then we know the cell design, the manufacturing quality, and the test data for every cell we build. And for every cell we build, basically in every cycle, every charge and discharge, 24/7, we have a very accurate prediction of the remaining useful life. If we didn't have this, we would not feel confident to scale up the line from A sample to B sample. It's this information access that we have.
Great. I think given the time, let's go to a few of these audience questions, because we've got a ton of them. In fact, 14 audience questions we've got already. So first one I'm going to go is to my friend Greg Yakovlev from Delft 25, who asks, with regards to the results presented for the 50 amp hour and 100 amp hour cells, is any external pressure applied?
There is, and then you could see the even the safety test. We do apply the cell under this clamp. We cannot disclose the pressure, and actually it's not one value; it's a dynamic value, and then it's a pressure that's acceptable to the OEMs. So it's not a crazy value that the OEMs cannot build a pack to apply this pressure. It's reasonable, and then I mean, for safety tests, we actually did safety tests with and without the clamps, but then just in this report, we show safety tests with the clamps, just because the OEMs ask us to do the safety test under the same conditions that we test the cells. So we apply the pressure, but the pressure is a very important parameter, especially for lithium metal. Again, it's not a crazy value, but it's a very important feature that if you know how to control it, then that actually makes a big difference in the performance and safety of lithium metal.
I guess where that... Sorry, Billy, you go ahead, Billy.
Oh no, I was just running through the questions, but you go, Mark.
I was just going to ask a follow-on. I was just going to say, I guess where that pressure question is coming from is, some concern that, in particular, some of your competitors may use a very, very high pressure, which may add significant cost to the battery. And so I guess that's where it's coming from. Are you adding significant cost? Is it something you're saying this is within the vehicle OEMs what the expectations? So I presume not, but could you further comment on that and how you maybe compare to competitors in this field that I believe some of them use quite very excessive pressure in some cases?
Yeah. So the pressure is and the pressure depends a lot on how you charge, discharge, and the environment of the cell. So now that we are in B sample, basically what we do is we actually look at the cost of the pack, which includes the pressure, and that also includes the cell energy density. That also includes the cell format, and then from this pack level consideration, this cell design with this safety characteristic, with this set of pressure, this complete package is acceptable to the OEM design. That's what I meant.
And Qichao, just building up on this question, I think these cell level energy densities are really impressive. And I know that in your prior material that you've sent, you've constructed these cells into battery packs and actually implemented into vehicles, which is really exciting. Can you give an indication of some of the challenges with making a lithium metal battery pack and how the energy density numbers translate to a whole system? Because I think a lot of people have seen that with lithium ion, almost certainly that decreases as you make it into a pack. And it would be great to kind of get your insights in terms of how that might translate in lithium metal.
Yeah, and then we actually built a pack. We took 14 of these 100 amp hour cells. We took 14 of these, connected them, and then we built a pack, and we put this in a drone. So yes, when you go from the cell level to this pack level, you do lose energy density. Currently, for this early design, we're talking about roughly 75 to 80%. The pack level energy density, and this is full pack. This includes BMS, chips, cooling, everything. 75 to 80% compared to the cell level, and the pack level performance is actually quite similar to lithium metal. So a lot of the considerations are similar to lithium ion. For example, you have to allow for cooling, heating, just uniform thermal feature, and then also there are some unique features that you have to consider for lithium metal. One is expansion. For example, these cells, depending on how you charge and discharge it, from 0% SOC to 100% SOC, there's a swelling of about 10 to 15%, and then so you do have to take that into consideration. And also at the pack level, depending on the final application, if it's a drone, then you have to use very light material, and then if it's a submarine, underwater vehicle, or if it's a land-based vehicle, then you want to minimize the volume. So you would use different materials and different weight, different strength for the final application.
Okay, great. And that maybe segues into two questions from the audience. Rory McNutley from Benchmark Minerals Intelligence, who asked, with these exciting new cells, where do you see the first market? Because you just mentioned a few different ones. Do you think it'll be luxury, mass market? And then he also asks about the supply chain for lithium metal, where maybe that isn't as mature as lithium ion with some of the materials. I don't know what your reflections on that are.
So I think in terms of first market, I think drones and UAM, flying cars. And even if UAM itself may not be certified, but the battery supply to them actually will happen quite soon. And then in terms of land-based vehicles, pickup trucks and SUVs, these actually, so these these cars tend to be really heavy with lithium ion, and then if we can lighten the weight, then that significantly increases the range, and also you can add more passengers. And then in terms of supply chain, lithium metal is actually very similar to lithium ion. So the cathode is the same supply chain. And electrolyte separator, these are not that different. The key difference is the lithium metal, the pure lithium metal. And that's obviously different from graphite. But actually, even in lithium ion today, many lithium ion companies are also using lithium metal for pre-lithiation to overcome the initial loss of irreversible capacity. So even lithium ion battery companies today are starting to use lithium metal. This lithium metal is a relatively more nascent supply chain compared to the other parts of lithium ion. But it's not like it's totally new. Basically, we take lithium ingots, and there are suppliers around the world in North America, South America, Australia that produce lithium ingots, and then there are different techniques to process lithium ingots into thin lithium foil. So it's not that new, and both lithium metal and lithium ion are actually working together to expand the lithium metal supply chain.
Great. One more question here, a question from Joseph Goodman from Volo Earth Ventures, also related to cycle life. Will you provide statistical data representative of production, or is the data we are looking at hero cell data?
Yeah, so the data that we are reporting are average data. We don't report hero data. We just report one, but we typically report the average data, and then most of the performance, because the cells we produce are quite consistent. For example, if you take 10 or 20 cells and then you same design, you run through the same test, basically the data will basically overlap on top of each other. It's the statistical variance of these cells onto the same test is very small.
And another question from Khan Kurtulus from Eaton Technologies. Why was the 50 amp hour cell chosen to receive IAFT certification, but not the 100 amp hour one, which seems to be the one that cell OEMs will likely go for?
Yeah, actually, we're doing that, and it's just a paperwork and process. So we can add that later. Yeah,
I see. Got it. And another question here from Serkan Savinch. Sorry if I got your name wrong. From the Charisma Institute. Can you give some details about the cathode and anode technologies, such as coating on the lithium?
Wait, so the question is details on the cathode and anode, and also the lithium coating?
Yeah, I mean, just he's asking, I mean, you've already talked about a lot of this before, but specifically he's saying details about the cathode and anode, such as coating on the lithium, anything else you can talk about
I see.
on both the cathode and anode side.
Yeah, so the lithium coating, obviously that's a proprietary material. We can't get into too much details, but the cathode choice, I can talk more. It's actually very interesting. So this chemistry, lithium metal, is fairly cathode agnostic. So for some OEMs that want to target high-end, long-range vehicles, then we will use high nickel NCM or NCMA, 80%, 88%. For some OEMs that actually don't want to use this chemistry for the high-end vehicles, but want to use this for the economy vehicles and then further lower the price, then actually we will use LFP. LFP paired with lithium metal is very interesting, because LFP paired with lithium metal gives you about the same energy density as high nickel lithium ion. So you have this very similar energy density, but LFP is much safer than the high nickel, and cheaper. So you end up with LFP lithium metal and high nickel lithium ion. Lithium metal is actually cheaper, safer. And at the pack level, that lithium metal, that LFP lithium metal is actually cheaper because it's safer and the material itself is cheaper. So we do have different versions of lithium metal that we are actively developing for the 3 OEMs to target different segments.
Mhm,
Qichao, on this point around cell configuration, I appreciate there's some commercial sensitivity, so you don't need to mention. But one of the things that various companies have reported is the cathode loading, which gives you an indication of, how energy dense it is. Can you maybe comment on what that is for SCS? Because I suspect that will be quite important because lithium metal is quite different from lithium ion, that the cathode loading also influences the lifetime on the lithium metal side.
Yeah, it does. And our cathode loading is around 4. That's fairly typical with lithium ion, and you almost have to achieve. So yes, if you go higher, the cycle life is lower, but then it's also, it's not just a cathode loading, right? It's like the ratio between the cathode loading, the how thick the lithium is, your charge rate, the amount of electrolyte, the whole consideration. But the cathode loading is important. If it's too thin, then the car becomes too expensive, and the battery becomes too expensive. And there is a minimal cathode loading that you have to be above, so that the cathode, the cost of the cell is competitive.
Another question here. I think you've already touched on this, but a question from Rory McNulty from Benchmark Mineral Intelligence. Qichao made a great point that B sample OEMs are now deciding what model SES cells will go in. Do you expect these first vehicles to be targeted at luxury markets or mass market?
So both, I wouldn't say luxury markets, because actually the 3 OEMs we're working with are not really luxury brands. So they both pickup, SUV, these large vehicles, large heavy vehicles, where if you can reduce the weight of the battery pack, then you can significantly increase the range and payload. And also economy vehicles, because when lithium metal pair with LFP, the battery is safer and cheaper, but still the same energy density as a high nickel lithium ion. That point needs to be stressed. So lithium metal for these pickup SUVs can increase the range and payload. At the same time, lithium metal for economy, when paired with LFP, can lower the cost and keep the range the same. So we have different vehicle programs.
There's 2 questions here about electrolytes. What type of electrolytes do you use? Specifically, what type of electrolytes do these cells hold to pass the nail pen test? Ionic liquids or polymer electrolytes? And can you talk about a separate but related question? Can you talk about electrolyte chemistry and its cost?
Yes, we can talk about electrolytes. That's quite key. I mean, it's a really exciting area. We have probably the best electrolyte team in the world working on this. We're also employing some deep learning to develop new solvent structures for the electrolyte. That part is really key. In terms of passing the safety test, that's more at a cell system level. Obviously, the material, the electrolyte, the cathode material, cathode plays a really important role in the safety and your cell design. There is a lot of engineering. And also in lithium ion, I mean, high nickel lithium ion has already been commercialized and then already meets the safety requirement, and there's a lot of engineering work that went into making a high nickel lithium ion safe. And so we borrow a lot from lithium ion industry, how they made the high nickel cathode safe. At the same time, we also develop our own safety approach to make the separator, the electrolyte, and the lithium metal anode safe. So it's a combination of material and also engineering. Actually, a lot of engineering, and especially when it comes to solving the safety, we actually prefer the engineering approach a lot more, because the material, when you change the material, sometimes you always have some trade-off, like you improve safety, but then something is worse. But when you have these engineering approach, you improve safety and you actually don't lose much in the other aspects. The engineering approach is actually very preferred, especially for improving the safety.
Okay, we are running out of time. I'm going to ask maybe time for one more question. Let's see how we go. Question here from John Harris. US tax incentives have recently changed. I guess he's talking here about not just tax incentives, but subsidies and IRA, et cetera, et cetera. I think your B samples are now made in Korea and China. Are you planning for mass manufacture within the borders of the US? And if so, do you have any specific venues in mind, or how are you thinking about location going forwards?
Yeah. So the A sample and B samples, the location is actually jointly decided between us and the OEM. It's not like we just exclusively decide to build it here. It's a joint development. So we jointly decide the location, and the A sample, B sample, C sample, these are pre-commercial. So these wouldn't qualify for the IRA anyways, because it's not a commercial sale. And so that is less of a concern. But once we get to C, then we do plan to produce these in the US or FTA countries. And in Korea, we have a lot of plans, both for EV and also UAM. We are setting up lines in Korea for EV B sample as well as UAM cell supply. And then Korea, things are quite efficient. The supply chain is quite mature, and it's a US FTA country. And then once we get to C sample, then we'll see. It'll be a joint decision. Again, the location of the manufacturing is always a joint decision between the battery maker and the OEM. It's not a one side decision by us.
Okay, great. I think we're about out of time because we're just hitting the top of the hour, so that makes us at the full hour. There are a lot more questions we didn't get to. Before I just wrap up, Billy, were there any more questions that you thought were important that you'd like to touch upon before we wrap up?
My final reflections is more to look to the future and ask Qichao, it's great to have achieved your B sample, but where do you see the foreseeable challenges in the future as you go to the next stages, and what are your plans to overcome that?
So I think performance and safety, these are always the two key things. Performance, I think we are probably we are the best in terms of lithium metal performance. And to improve that performance, basically we're doing things that no one has done before. It's not like you can copy someone. There's no one to copy. So trying to hire the best talent, best scientists, best engineers to basically invent new things, come up with new ideas. That's very challenging. We are trying to supplement this human effort with deep learning, and hopefully we'll see more results in the coming year. I mean, using deep learning to explore new materials for batteries, electrolytes, it's very exciting. It's really exciting. I mean, some of the early signals that we're seeing is very interesting. So maybe if our human scientists can come up with a higher Coulombic efficiency electrolyte, maybe the deep learning model will in 6 months to 9 months. So that's on the performance side. Safety is a very complex topic, because it's not just cell level safety, it's not just material level safety, it's not just fresh cell safety, it's cycle cell safety, and then safety has to do with material design, the cell design. It also has a lot to do with manufacturing quality. And then when we just entered A sample and then started making these 100 amp hour cells, just 100 of these cells per month, and then to 1,000 of these cells per month, and then running multiple lines, and then now B sample, several thousand of these cells, multiple lines. And this manufacturing quality, this control plan is really important. And then we have very fragmented control plan in the past. Now we are working to standardize and then unify, and then knowing what we're making, like having a very detailed set of data, and then being able to collect the data and make sense of the data and process the data, that's really important. I mean, the volume that we're making isn't that high, but then it's a totally new chemistry, it's a totally new technology. So even if it's a small set of data, we can actually learn a lot. For example, I mentioned that we had 25 incidents over the past 2 years with these big cells. And we actually learn more from these 25 incidents than the cells that were good. And last year, 2022, our ability to predict these large cells was only 60% avatar prediction. Now we can predict 23 out of 25 cells, 92%. So all these data transfer to our learning, and then with this learning, then we can really improve the safety. So I would say the biggest challenge just wrapped up in improving the performance beyond anyone has done before, and improving the safety, and just having a really good information and knowing what we're making.
Perfect.
Sorry, I was just on mute. And with that, I'd just like to thank everyone for joining. Specifically, like to thank Qichao, of course, for presenting this data to us, to Billy for joining and helping ask much smarter questions than I could come up with. Also, thanks to Yen and Volta for hosting this event. Reminder again that the Battery World 2023 is on December 12th. There are details now in the chat function at the bottom. You should be able to see that. Again, if you don't have that, you can find it on SES website, SES AI website, or reach out to one of us. And with that, again, thanks all for joining. And any final comments from you, Qichao, before we wrap up?
No, I mean, again, thanks Mark and Billy for this discussion, and also thank Volta for hosting. This is I think year 3, and hope we can keep doing this. And yeah, so the significance of this B sample is actually, obviously from a commercial perspective, we are one step closer to commercializing lithium metal. But then also it's all the progress that we have made, and all the progress that we have yet to make. And then the areas cover materials, developing new materials to improve the performance, and the use of deep learning, And I mean, deep learning is now used in the pharmaceutical industry, and it has shown a lot of progress in drug discovery. And we are just in early stage, but we're seeing very exciting signals from the work that we're doing. And I think in 2024, maybe 6 to 9 months from now, we'll see something very interesting. And then this manufacturing, before we got into A sample and then now B sample, we didn't really know the challenges that lie in the manufacturing, and it's very complex. Different OEMs want different dimensions, different designs. But then we learned in the past a year to 2 years that the foundation is really important, and the foundation is the control plan. The control plan is the foundation to building these high-rise buildings. I mean, doesn't matter how you design the high-rise buildings, but once you have a solid control plan, then you know what you're making. And this control plan is the core to our Avatar, which is this software that allows us to predict remaining useful life and safety. And we expanded our manufacturing capability, testing capability, so now we can test the new ideas, new chemistries under different conditions, and then that also help us to make the control plan even more rigorous, and then tie that to Avatar. So to us, manufacturing and this safety is really important, and the core is in having a rigorous framework called control plan that we can collect all the information. So going forward, this lithium metal, I think we're definitely one step closer to EV. And then in addition to EV, we'll also announce new markets, one of which is urban air mobility, UAM. And for example, we just tested lithium metal in under UAM conditions. It's 1,500 cycles, so it's a very good fit for UAM, and we'll probably see lithium metal being commercialized in UAM around the same time as EV, if not earlier. So, yeah.
Great. Well, thanks for that, Qichao. Thanks everyone for joining, and please join us for Battery World 2023. Have a good day.
Thank you, guys. Thank you.